This lesson is on rational functions and some terms to know. What's a rational function? It's a function that has x in the denominator. What's the domain? We should know that. That's the set of x coordinates. We're going to look at horizontal intercepts, also known as x-intercepts. You know that. You set y equal to 0 to get that. Vertical intercept, that means y-intercept. You set x equal to 0 to get that. Horizontal asymptote, that's in the form of y equals some number k. Vertical asymptote, that's in the form of some number x equals h. A hole is a point that doesn't exist, but we can state the location of the point. So it's an ordered pair in the form of xy. So to start this lesson, we're going to go back to Unit 1 ideas and look at the graph to answer the questions and then see how it relates to the equation. So we have this first example. This is a rational function. It has two branches on the outside and this down-down graph here in the middle, and it's got dashed lines that you can see right through here and a dashed line there. So first question is, what is the x-intercept? Well, the x-intercept is the place where the graph crosses the x-axis. So that happens here and here, and we're counting by ones, so -3, 0 and 2, 0 are x-intercepts. Now look at the function. Where do you think this -3 comes from? Where do you think this 2 comes from when you're looking at the equation? Alright, next we have y-intercept, and we're counting by ones on the y-axis, and it's not quite 1. We're going to have to estimate that, maybe 0.9. Now you get the y-intercept, by putting x into putting 0 in for x. So if we put 0 in for x, we get 3 times -2 times 3 divided by 4 times -5. So let's figure out what that is. See how close we came. So we have 3 times -2 times 3 over 4 times -5. Oh, I was right on that. I did not expect that. I was right on 9/10. Alright, now look very carefully, see if there's a hole. And I don't see a hole. So there's none. A vertical asymptote, looks like we have two. One here. This is x equals -4. Remember, it's a vertical line, so we need vertical line notation. And we have another vertical asymptote at x equals 5. Take a look at those values and look at the equation and see if you can tell where that comes from. It seems to come from the denominator. Alright, there's a horizontal asymptote right here when y is 3, so y equals 3 is the horizontal asymptote. Notice that the horizontal asymptote doesn't have the restrictions on it that vertical asymptotes have. You'll never cross over a vertical asymptote because these are the things that x can't be. But a horizontal asymptote is about end behavior. So as x gets really, really large, it's going to hug that horizontal asymptote. But for small values, it might even cross over it. Okay, the domain of f of x. Well, if we just look at the graph, you can see that it starts out at -infinity. The x values, -infinity, seems to be not wanting to hit -4, union. -4 seems like it's good until we get to 5. Skip over 5 and then start back over to infinity. So what's the relationship between the vertical asymptote and the domain? Just a little discovery here. Alright, let's look at this graph. This is a more typical rational function. 2 branches, 1 vertical asymptote. Looks like it has a horizontal asymptote right here. So let's start with the x-intercepts. Looks like this doesn't cross the x-axis at all. Alright, the y-intercept Again, y-intercept's a little bit harder to find, so that's 1, that's negative 1, that's negative 2. I'm going to say negative 1.8. But we find it by putting 0 in for x. So let's see if we can figure out what that is. So if we have 5 parentheses 4 divided by, negative 3 times 4, I'm put 0 in doing some mental work here, I get 5/3, and that is negative 1.67, or negative 1 2/3. So it wasn't quite right there. Alright, let's see if we can find a hole. It seems like there's a hole there when x is negative 4 and y is not quite negative 1. I'm going to say negative 0.9 again. It's just a guess. We're looking at the graph. The vertical asymptote going through when x is 3, so the vertical asymptote is x equals 3. Horizontal asymptote looks like it's this x-axis, so that's y equals 0. Alright, and the domain, all the set of x coordinates that give you bordered pairs. Okay, so this is a little tricky. You got negative infinity. All these x coordinates are giving you y coordinates, ordered pairs, but then when you get here, that's not a point, that's a hole. So we've got to skip over when x is negative 4. And then negative 4 all the way to 3, but then we have to skip over that vertical asymptote. Alright, now take a look at your denominator. Negative 4, x plus 4, 3, x minus 3. But where does that hole come about? Well, that's what we're going to talk about. Alright, so before we move on, just give yourself a chance to try that with these. And these are some really crazy looking rationals, but you just look at the graph and see if you can write down the following, and I'll come back and reveal the answers and then we'll move on. Okay, here's what I got. I got x-intercepts negative 7, 0, and 3, 0, and they come from this factor here and this factor here. And where did that go? Why isn't there an x-intercept at negative 2? We'll come back to that question. Y-intercept, there is none. And then there's a hole at approximately negative 2, and I said about 8.2. That's approximate. Alright, so where do holes come from when you're looking at the equation? Well, notice that this x plus 2 was not an x-intercept, and that is because there is an x plus 2 in the denominator, and they cancel out. Okay, so if those factors in the numerator and denominator cancel out, that doesn't give you a vertical asymptote, it gives you a hole. And then you have to plug negative 2 into the remaining factors to see what that answer is. So I'll check my work to see what I got. So I'm going to put in negative 2 plus 7, because when we know x is negative 2, we're trying to figure out what y is, times negative 2 minus 3 over negative 2 minus 1. And 25 over 5 is 8 1/3. Okay, so the whole is exactly negative 2, 8 1/3. Alright, vertical asymptote, x equal 1. There is no horizontal asymptote. Now, the domain comes from the denominator before you cancel. Because this vertical asymptote and this hole, these both come from the restrictions. They're just different types. So x can't be 1 and x can't be negative 2 shows up in the domain. Okay, let's look at the next one. And I got x-intercepts negative 3, 0 and 2, 0. Okay, but the x-intercepts come from the numerator, so what's happening with this one? Well, this one is the same as that one. So that's like x minus 2 quantity squared with a multiplicity of 2. And look right here, notice that there's a bounce. So that's making sense from a previous lesson. So there's those two x-intercepts. The y-intercept I said was about 0 2/3. Let's check it and see exactly what the equation gives us. So -3 times -2 times 3 times -2 divided by 5 times 2 times -6. I've put 0 in there. And I get 3/5, which is 0.6. So it wasn't that far off, but let's be accurate here, so we'll write that down. Alright, so we got that by plugging 0 in. There is no whole. Notice that nothing canceled. None of the factors canceled, so therefore no whole. There are 3 vertical asymptotes, one from this denominator's factor, -5, this one, x equals -2, and this one, x equals 6. The horizontal asymptote, you can see right here, and we haven't talked about where that comes from yet. See that -3 in the top there? And the degree is 1, 2, 3 over degree 3. That's where that horizontal asymptote comes from. We'll talk more about that. And then the domain is all the restrictions that comes from the denominator. So the domain is -∞ to -5, union -5 to -2, union -2 to 6, union 6 to infinity. Okay, so now let's look at Unit 2 idea. Given a rational function, be able to find all the things that we just found where we were looking at the graph. Okay, so here is a rational function. I left off the f of x. Let me put that in there. And notice that it is not factored. Well, step 1 is you have to factor that. And so all the previous examples were already factored. So if I factor x squared minus 16, that's going to factor into x plus 4 times x minus 4, because that's a difference of 2 squares. X squared minus 7x plus 12 will factor. There's an x here and an x here. We want to check the factors of 12. 1 and 12, 2 and 6, 3 and 4. That add up to be 7, and that's 3 and 4. And we want them to add it to be a -7, so that's x minus 3, x minus 4. So step 1 is you definitely want to factor. Okay. Step 2, before you do any canceling, which I kind of mentioned before, and now we're going to really look at it. Before you do any canceling, you want to find the domain. The domain happens before any canceling, and the domain comes from the denominator. So if you set each of these factors equal to 0, you get x cannot be 3, or they can't be 0, sorry. And x minus 4 cannot equal 0, you get x cannot be 4. Okay, so the domain is going to have to hop over those restrictions. Okay, so in interval notation, the domain is from -∞ to 3, hop over 3, 3 to 4, hop over 4, 4 to infinity. All right, now that you've written down the domain, if you've written down the restrictions, now it's time to look and see if you can cancel anything. These restrictions are going to show up as either vertical asymptotes or wholes. Okay, so if you look here, notice that the factors x minus 4 cancel. Okay, that's going to turn that restriction x cannot equal 4 into a whole, and a whole shows up as an ordered pair. Okay, so how do you find that y-coordinate partner with that whole? Well, this rational function, before I canceled out the x minus 4, is going to look just like this rational function without the x minus 4, except this rational function is going to have a whole at this point. So all you have to do, and I say all you have to do, but students struggle with it, is plug that 4 into this function here after you cancel. So we've done that. Just use your calculator. So we have 4 plus 4 divided by 4 minus 3. I just plug 4 right into that function. And that gives you 8. So the whole is 4/8. That means there's an open circle right there on the graph. This graph, if you were this graph and this graph look exactly alike, except this one does not have a hole and this one does. Okay. All right, so vertical asymptote, we've taken care of the restriction at 4. This x minus 3 factor did not cancel, so that means there is a vertical asymptote at x equals 3. So all three of these come from looking at the denominator. Remember, you have to find the domain first before you do any canceling. Next concept, it's a different concept, is the horizontal or slant asymptote. Now in this unit we don't even worry about the slant asymptote. So a horizontal asymptote is about end behavior. For large values of x, what happens? So that is about degree. We've talked about degree before. So this actually is easier to see when you're looking at the unfactored equation, because if it's multiplied out, remember the leading term has the greatest influence on end behavior. So this has the same degree. All right, so if you're looking for the horizontal asymptote, I wrote it all out here. If you've got the same degree n over degree n, see that n and n, then the horizontal asymptote is just going to head towards this k over this h. All right, so that's what we have here. We have the same degree, so the horizontal asymptote is going to be y equals 1 divided by 1, which is y equals 1. All right, now the y-intercept, you've known this. You just find it by setting x equal to 0. And you have to use either the reduced equation, which is right here, or this equation. But you can put 0 in either equation, because this equation and that equation are going to be exactly the same. They're going to have the same y-intercept, except this one has a hole. Okay, so if I put 0 in here, I get negative 16. So let me put 0 comma, you get negative 16 over, if I put 0 in here, I get 0, 0, and then I get 12, and that reduces, and you have to reduce to 0, negative 4/3. So that's your y-intercept. The x-intercepts have a nice little trick for you. All you have to do is look at the numerator. Set the numerator equal to 0. So this factor's gone. So x plus 4 equals 0 gives me an x-intercept of negative 4, 0. Okay, that's our first example, and we found all of those points just by looking at the equation. Let's do another one. Okay, so f of x equals x squared minus x minus 30 over x minus, that's a plus, x plus 5. First thing we have to do is factor that top. So that's going to be x and x. And the factors of 30, 1 and 30, 2 and 15, 3 and 10, 5 and 6. Have to subtract to be negative 1. That's 5 and 6. We want it to be a negative 1, so negative 6 and positive 5 over x plus 5. So step 1, you factor. Before you cancel, now you may get overzealous and think, oh, these cancel. Before you cancel, you have to find the domain. And the domain comes from the denominator. So set the denominator not equal to 0, and you get x cannot equal negative 5, which is going to show up in interval notation as negative infinity to negative 5 union negative 5 to infinity. Okay, now you look to see if you can cancel, and they cancel. So my reduced function is f of x equals x minus 6, but there is a hole. This restriction is going to show up as a hole at negative 5 something. Right? This is the equation that you use to get it. If you put negative 5 in for x, the y-coordinate partner is negative 11. So this is the hole for this rational function. And once you cancel these factors, there is nothing left in the denominator. There is only one restriction. So this one doesn't have any vertical asymptote. Different concept for horizontal or slant asymptote. You look at the degree. So let's look at this one. This degree here is degree 2 over degree 1. Let's go back on the other side and see what we have here. So if we have degree large over degree small, then there is no horizontal asymptote. There's going to be something called a slant asymptote, and we're going to use long division to get it, but that's not in this unit. So all we have to say here is that if you have a degree large over small, there is no leveling off. There is no horizontal asymptote. And while I'm here, if you have a degree small over large, then the horizontal asymptote will be y equals 0. Degree large 2 over degree large 1, so there is no horizontal asymptote. Okay, to find the y-intercept, you put 0 in for x. So if we put 0 in for x, we get 0, negative 6. And I just use the reduced function. Okay, the x-intercept, remember my trick is you just look at the numerator. So there is a x-intercept at 6, 0. All right, now we can graph these. So let's graph the points first. So it looks like we're counting by ones, which is a little bit harder because we have to go down here to negative 6, 0, negative 6, and then we have to go over here to 6, 0, and we have a hole at negative 5, which all the way down to negative 11. I'm just going to sketch it. All right, and then that's it. That's all we have, but we know what y equals x minus 6 looks like. That's a line. Alright, so we're just going to connect those dots. So sometimes our rational functions can look like lines if the factors cancel. This is a line with a hole in it. Alright, let's look at another example. So this one is a little bit harder to factor because you have a 2. Sorry about the focus. And so we have to do a little bit more work here, and we have to think about how to factor. It's going to factor into 2 binomials. At least this 2 is prime, so I know 2x and x go here. And I have to check the factors of 6. 1 and 6, 2 and 3. This time I can't just see which one to subtract to give me 1 because it's not x and x, it's 2x and x. So remember, you have to check your outer and your inner terms. It's usually a good idea to check the ones closer together. So I'm going to put a 2 here and a 3 here and see. That gives me 4x. That gives me 3x. Do they subtract to give me 1? They do. Last thing, I want it to be a negative 1, so I'm going to need the 4 to be negative and the 3x to be positive. So the 4x comes from 2x plus 2, so that's negative, and the 3x comes from 3 times x, so that's positive. Okay, I'm going to erase that. So this factors into 2x plus 3 over x minus 2, and then we have an x plus 3 in the denominator. Okay, I've moved these boxes around just because I want you to know that the hole and the vertical asymptote actually come from the domain restrictions. First thing we have to find is the domain. We look at the denominator. We find out x cannot equal negative 3. So in interval notation, we get that. Then we look to see if any of the factors cancel, and they do not. So since none of the factors cancel, there is no hole. Okay. So the vertical asymptote is going to show up, the restriction is going to show up as x equal negative 3. It comes from the denominator, comes from the restriction on the domain. Horizontal asymptote, you look at the degrees. So we have degree 2 over degree 1, degree large over degree small. That means there is no horizontal asymptote. The y-intercept, you set x equal to 0. And I always think it's easier to use the multiplied out function because if you put 0 in for the x's, you're left with negative 6 in the top over 3, so that's 0, negative 2. Alright, now the x-intercept, you set the numerator equal to 0. It's better to use the factored form. So if I set 2x plus 3 times x minus 2 equal to 0 and find these zeros, 2x plus 3 equals 0 when x is negative 3 over 2, and x minus 2 equals 0 when x is 2. So this one has 2 x-intercepts. And that's all the stuff. Let's move on to practice number 3. See, x squared minus 9 factors into x plus 3, x minus 3. X squared plus 5x plus 6. The factors of 6 are 1 and 6, 2 and 3, but they need to add to be 5. So don't pick 1 and 6, they subtract to be 5. 2 and 3 add to be 5. Okay, so factor first. Then you're going to find the domain. So the domain, you look at the denominator, x cannot be negative 3, x cannot be negative 2. So the domain is negative infinity to negative 3 union negative 3 to negative 2 union negative 2 to infinity. After you get the domain, that's when you look and see if you can cancel factors, and these x plus 3 factors cancel. That means you're going to have a whole at negative 3 something. Okay, so let me write down the reduced function. The reduced function is x minus 3, x plus 2, and that's what you use to find the whole. This function and this function look exactly the same, except there's a whole. So if I plug negative 3 in for x to find the y-coordinate partner, using this reduced function, negative 3 minus 3 over negative 3 plus 2, I get nice 6. So there is a whole at 3, 6. Okay, now the vertical asymptote, so that restriction is taken care of. The vertical asymptote comes from the factor in the denominator that does not cancel, and it's the equation of the vertical line, x equal negative 2. So all those things kind of work together. All right, the horizontal asymptote is about degree. Degree 2 over degree 2. So if it's the same degree, the horizontal asymptote is going to be y equals 1 over 1. Remember, these two functions look exactly the same except for the whole. So this works here. You can look at the reduced function. Degree 1 over degree 1, same degree, 1 divided by 1, y equals 1. The y-intercept, you can use either function. Okay, so all you have to remember is that you have to put 0 in for x. So if I put 0 in for x, I get negative 9 over 6. See that? That reduces to negative 3 over 2. Doesn't matter which function you use. The x-intercept, you look at the numerator. So that's better to look at the factored form, but either one, and you get 3, 0.